Good afternoon, madam. Shall we start?
Okay, sir. Start recording, sir. So good afternoon, guys. Now we will do some more problems in the counters. Right. So your question is design a decade counter. Design a decade counter. Design a decade counter using T flip flop. Design a decade counter using T flip flop. Design a decade counter using T flip flop. That is your question. Design a decade counter using T flip flop. Okay. So decade is nothing but mod 10 counter. Decade is nothing but mod 10 counter. Design a mod 10 counter using T flip flop. That is your question. We'll start working on that. So, what is the capital F here? What is capital F here? For decade counter, mod 10. What is capital F here? N is equal to 10, right? So, 2 raised to n greater than or is equal to capital N. So, 2 raised to n greater than or is equal to 10. What is the value of small n? How many flip-flops are required here? What is the value of small n? How many flip-flops are required here? How many flip-flops required in this condition? Mod 10 counter, how many flip-flops required? Sir, am I audible, sir?
You are audible, madam. No issues. You can proceed.
Hello? Am I audible?
Yes, madam. You are audible. You can proceed. Madam, you are audible. Please proceed.
Okay, sir, okay. Because I am not getting any response. What is the value of number of flip-flops here? This is equal to 4, right? So 2 raised to 4 is nothing but 16. Okay, 16 will be greater than or is equal to 10. So you are using 4 flip-flops, right? So how to write the table here? Present state, next state, then flip-flops input. Okay, this is what you are writing. So 4 flip-flops is required, so you can put it as D, C, B, A. Okay, these are the 4 flip-flops you are using. So the next step will be D plus 1, C plus 1, B plus 1 and A plus 1. Okay, you are using T flip-flops here, right? You are using T flip-flop here. So how to name that one? T flip-flop. T flip-flop will be T D, T C, T B, T A. Okay. So totally, mod 10 means totally 10 states will be there. Okay, it is not the number 10, only 10 states. So you are starting from 0, 0, 0, 0, 0, then is 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. 0, 1, 1, 1, then 1, 0, 0. So how many states? 1, 2, 3, 4, 5, 6, 7, 8, 9. So one more state is required. So 1, 0, 0, 1. So whatever be the next state, all those things will be non-air conditional. Okay. So what is the next state here? So total 10, right? 0 to 1, then 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 0. It is back to 0, right? So that is the next state will be. So 0, 0, next state will be 0, 0, 0, 1, then 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, then 1, 0, 0, 1, then after 1, 0, 0, 1, what is the next state? That is 0. Okay, it is again back to 0, 0, 0, 0. Right. Now, what you have to do is you have to write the input for the state for corresponding to T flip-flop input. Okay, you have to define the flip-flop input from the present state and next state. So, someone please, okay, you can post messages like what is the next flip-flop input for TD flip-flop, okay, D flip-flop. You have to find out the input, flip-flop input for D flip-flop. From this table, this is the D present state and this is your D next state. So from this, you have to find out what is the input for D flip-flop. My question clear? Is that clear? Is that clear? Why voice is not clear?
Madam, can you repeat the question once again? Madam, can you repeat the question once again?
Is my question clear? You have present state of input, then you have next state of input, and your question is design using T flip-flop. Okay. So design using T flip-flop, you have to find out what is the input for the all the four flip-flop from the present state and next state. You have to define what is the flip-flop input. So this one you can write it because I'm just continuing. So this is 0, 0, 0, 0. Next will be this is 0, 0, 0, 1, and this one is 0, 1. Okay. And what about for PC? This is 0, 0, 0, 1. Then here also 0, 0, 0, 1. And the last one is 0, 0. And for TV, this is 0, 1, 0, 1. Then here also 0, 1, 0, 1. These are 0, 0. Then for PA, all are 1. Okay. 1, 1. This is the answer. Okay. Any deviation in this answer? If you have any deviation, please let me know. If you have any deviation, please let me know. If you have any deviation, please let me know. Whether it is correct or not. Is it correct? TB, TC, TB, TA. Is it correct? Any deviation? Is that right? You post at least one yes or no. It would be very difficult to be here. Okay, there is no response. Okay, so what is the next step? Using K-map, you have to find out what is the value of TA because these are just digits are given, right? So we have to find out the corresponding solution, right? So using K-map, first one is for TD. What about this one? So totally 10 is there. So it is 4 variable came up. You have to know the 4 variable came up. And this one is B, C, D, A. This is B bar, A bar, B bar A, B A, B A bar. This is D bar, C bar, D bar C, D C, D C bar, 0, 1, 3, 2. 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Okay. So how to put those numbers here? Because this is corresponding to this is M0, M1, M2, M3, M4, M5, M6, M7, M8, M9. Okay, only up to M9 we have. We don't have other numbers, so you can put the dot pairs for others. Right. So this is 0, 1, 2, 3 is 0, 0, 0, 0, 0. Then what is next here? 4, 5, 6, 7. 7 is 1, 4, 5, and 4, 5, 6 are 0. Right. Then 8 and 9, 9 is 1, 8 is 0. So and all other conditions are non-pair conditions. Right. This is what. Then what is the value of TD? What is the value of TD? What is the expression for TD? You can make a part here and you can make a pair here, right? So your answer will be, what is this one? This is CDA, right? CDA plus, then what about this part? Here D is common and here A is common. So which is equal to D A. Okay. TD is equal to CBA plus BA. So any objection in the answer? Is there any objection? Or is it correct? No objections, okay. So next similarly, TC you have to find out. So the answer is BA. Okay. And TB, your answer is A, B bar. Okay. So similarly, and TA is equal to 1. This is your answer. Okay. So you have to verify all those things using K-bar. And if you are not getting these answers, please let us know. Right. So this is while doing simplification using K-bar, you will get TC is equal to BA. Okay. This is BA and T. This is B. Okay. TB is equal to A B bar and TA is equal to 1. Right. This is what we are getting. Now what we have to do? We have to draw the diagram. We want to draw the circle diagram. Right. Draw the circuit diagram. So we have to draw 4 flip-flops, right? This is TD, this is QD, QD bar, Then the second one is PC, this is QC bar. Third one is TB, this is QB bar. And the last flip-flop is TA, and this is QA bar, right? So all are synchronous sequential circuit only, synchronous counter only. So what you have to do? You have to connect all the flip-flop using same clockwise. Okay, you have to connect all the flip-flop using same. This is your clockwise. You have to use the same clockwise. Then now what we want to do? We want to find it out TD. TD is using a OR gate, right? You are using an OR gate here. So OR gate input has to AND gate output, right? First one is CBA. CBA is nothing but you have to draw. This is QA is connected. Then B, right? B you are connecting, and the last one is C. Okay, this is CBA. Then what is next one? Plus DA. DA you are connecting to here. D, and which one is A? The last one is A. Okay, A is connected here. Right. Then what about TC? TC is BA. TC input. But which one is B? This is B, and this one is A. This is A, B. Okay. Then what about the TB? AD bar. TB is equal to AD bar. A you can connect it from here. This is A. D bar you have to connect from here. Okay, this is D bar. This is TB, and the last one is TA, which is equal to 1. This is the circuit diagram we have to draw. Is that clear? So you can note down, and once you complete it, please let me know. Did you finish? Shall we move to the next question?
Yes, ma'am. We will proceed.
Sir, shall we proceed, sir?
Yes, madam. We will proceed. We will
Hello?
proceed, madam. Madam, we will proceed.
Shall we proceed? Okay. We'll do one more problem in this counter and then we'll move to the next topic after that. We'll move. So your question is design a synchronous counter using JK flip-flop. Design a synchronous counter using JK flip-flop and it has to count like this: 4 to 6, 7, 3, 1, 4. Okay, so this is the order. Okay, so after 1, it has to come back to again 4. This is the order. You have to count. You have to design a counter, synchronous counter using JK flip-flop. You have to design a synchronous counter using JK flip-flop for this first step. 4, 6, 7, 3, 1. This is the order. Okay, so you have to design the same using JK flip-flop. So how many states are here? So maximum state is 7, right? Here maximum state number is 7, right? So what you have to do? 2 raised to n, greater than is equal to n. So this is equal to 7. So you can write n is equal to 3. You need to use only 3 flip-flops, right? So again we are going to write the present state. Present state. Then second one is this is present state. Then next state. Then flip-flop input. Okay. And one more thing is here in this question they are asking for avoid lockout condition. Lockout condition. Avoid lockout condition. Okay, this is one more thing it was asked. Okay, so lockout condition means that is nothing but the state which is not here. Okay, some states which is not here. What you have to do is you have to find out the solution for that particular state. So here, what are the states here? 4, then 6, then 7. Then 3, then 1, again it is coming back to 4. Okay, so what are the missing states here? 0 is missing, then what is the next state missing? 2 is missing, then what is next step? 5 is missing. Okay, so all these 3 states are missing in this condition. Okay, in this question 0 is missing, 2 2 is missing and 5 is missing. All these three are missing in this condition. But in the previous counters, it is counting in the order. Okay, so it is counting in the 0, then 1, 2, 3, 4, 5. Then after that, once 5 is comes, then it is back to 0. It is based on the mode terminal, right? So here what is there? It has to count 4, next is 6, then 7, then it is count 3, then it is count 1, again it has to count 4. Okay. So what is happening in this condition? 0, 2, 5 are missing. So what you have to do is, so what is the next state of 0? The next state of 0 is 1. Then next state of 2 is equal to 3. The next state of 5 is equal to 6. So okay. So whenever the counter has this condition, it has to move to the next condition. This is our assumption what we are going to take. Okay. So it has to move to the next condition 1. So next highest state. So 0 here this is 0. 0 has to move to 1. Whenever 0 comes, it will be next state must be 1. That is, you are defining this condition. Okay, this is a condition which you are defining. Then what is next is 2? 2. This is 2. So next state is 3. Okay, and then for 5, next state is 6. Okay, whenever 5 comes, it is automatically moved to the next state of 6. So what you are going to write up here? So you require 3 flip-flops. You can put it as C, D, A. Here it is C plus 1, B plus 1, A plus 1. They are asking for JK flip-flop, right? So what you have to do? JC, KC, then JD, KD, then JA, KD. These are your flip-flop input. Okay, these are your flip-flop input. So you are going to write it in this order itself. So what is the first one? 0, 0, 0. Then 0, 0, 0, 1. 0, 0, 1. 0, sorry, 0, 1, 0. 0, 1, 1. Then what is next? 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. These are all the possible combinations of the 3 flip-flop, right? So first is 0, 0, 0. 0, what is the next state of 0? Next state of 0 is 1. Okay, so you have to write it as 0, 0, 1. Then what is the next state of 1? Next state of 1 is 4, right? So you have to write 4. What is 4? 0, 1, 1. 0, 1, 1 is nothing but 4. Then what is the next state of 2? Next state of 2 is 3. Okay, so what you are going to write? So this is not 4, this is 1, 0, 0 is 4. Okay, 0, 1, 1, 3. Then what is the next state of 3? Next state of 3 is 1. Okay, so again you are writing 0, 0, 0, 1. Next step. What is the next state of 4? Next state for 4 is 6. 6 is nothing but 1, 1, 0. Next is 5. 5, what is the next state of 5? That is also 6. So we are writing 1, 1, 0. Then what is the next state of 6? That is 7. So 1, 1, 1, that is 7. Then what is the next state of 7? That is 3. 3 is nothing but 0, 1, 1. So this way you have to write the next state based on the question given it. Okay, what is the requirement based on the question? Okay. Now you have to write the flip-flop input of for JC, KC, JB, KB, and JK. Is that clear? How to write? Is that clear? Is that clear? Is that clear? Now you have to find out the flip-flop input for JC, KC, JB, KB, and JK. So C is given 0. Next is taken C plus 1. That is also 0. So what is that? 0x or x plus x0. So JC KC this is equal to 0x 1x. That you have to find it out because in the morning session we have seen that only how to update this flip-flop input. So you have to find it out. Then this is 0x, 0x. This is x0, x0, x0. This is x1. So here it is 0x, 0x, x0, x1, 1x, 1x, x0, x0. Here it is 1x, x1, 1x, x0. This is 0x, x1, 1x, x0. If you have any doubt for writing this flip-flop input, please let me know now. Do you have any difficult to get the flip-flop input done? Do you know how to take that one? If you have any doubt, please let us know right now. Doubt irukka illaya? Please let us know how to take the flip-flop input if you have any doubt. Or yes or no போடுறது எப்பப்பா எவ்வளவு டைம்? No means what? No doubt. Yeah, there were. They have doubt. It's clear.
Darshini and Sedamadavan, is that no stands for no doubt or not able to understand? No doubt. Okay, fine. Thank you. Now we'll proceed.
Okay, sir. So what is the next step? You have to draw the schema and you have to find it out for JC, KC, JD, KB and JK. Okay. So this is for JC only we are showing here. So what is given in the question? CBA, right? So this is B bar A bar, B bar A. This is BA. BA bar, this is C bar, C. Okay, so we are going for writing for only JC. So this is equal to 0, 1, 0, 0. Then what is the second one? All are not pairs, right? All are not pairs. So what is JC? JC is equal to B bar A. JC is equal to B bar A. Right? Next one is similarly AC is equal to BA. Okay, AC is equal to BA. Then what is next? JB. JB is equal to C and AB is equal to C bar A. AB is equal to C bar A. Okay. And last one, JA is equal to C bar plus B and KA is equal to B bar. So if you have any doubt, please let us know. You have to draw the schema and you have to find out the solution. Okay. You have to draw the schema and you have to find out the solution. So only JC is given. Similar way, you have to draw the schema for KC, JB, KD, and JA and KD. So you will get these answers. You have to work it out and please tell me if there is any deviation. Shall we draw the circuit diagram? So you have three flip-flops. JC, KC, QC, QC bar, JB, KB, this is QB, QB bar, and the last one is JA, AA, QA, QA bar. So everything is, this is a synchronous counter. So the same clockwise you need to connect to all the counters, all the flip-flops. This is clockwise. So what is JC? JC is AB, right? So this is JC. Is connected to, this is QA, and this is nothing but AB, right? Then KC. KC is also equal to AB, right? First one is B bar, right? Okay, so this is QB bar. This QB bar, right? Then what about KC? KC is equal to AB. This is JC is equal to B bar A and KC is equal to AB. So A is connected here. So B we can connect it from here. Okay. Right. Then what about the JB? And JB is nothing but QC. C itself. Then KB is equal to C bar A. KB is equal to, this is C bar and A you can connect through here. Okay, this is KB. Then what about the JA? JA is equal to C bar plus D. So you are using an OR gate here. B is connected, then C bar, QC bar. We'll take it from here. Okay, this is C bar plus D. Then K is equal to B bar. This is the circuit diagram for circuit diagram asked in the question. Okay, so for counters, whatever it be, you have to draw the circuit diagram. Then only you will get the full mark. Okay. Shiva sir, are you taking now itself? If you want, you can take now itself, sir. No, how much time actually you require, sir? I think if no, I'll take one more problem. Then we'll finish two experiment today, sir. Then Saturday is the first hour, no? So we'll continue in one Saturday first hour.
I'll
Okay,
take
sir.
over.
Okay.
Okay. Madam, I suppose in both the.
1 second, sir. 1 second. 1 second.
Let me know.
Yes, sir. I can see you.
I think. Oh, okay. Good afternoon. To start with now, we'll just move ahead with two of the lab experiments, namely experiment number 5, which is to do the design and implementation of a magnitude comparator, right? So here in this experiment, what we are going to do is we are just trying to realize a magnitude comparator. Normally in our lab, we will be using a comparator IC, which is IC 7485 to do this operation. But right now, since we are going to simulate it on our thing, then we are planning to go ahead with logic gates, right? So let's practice with the logic gates. To know about the theory part of a magnitude comparator, it is a combination circuit, in fact, with the input signals and outcome. We are going to generate an output signal, which is going to tell us whether if both the inputs are equal, or one is lesser than the other, or the other is greater than the. Okay, so that's a purpose. That's a reason behind going for a magnitude comparator. Okay, and this IC7485, when we say it is an high-speed 4-bit magnitude comparator. Okay, when we say 4-bit and two inputs, each input will have 4 bits. Say, for example, if my inputs are A and B, then I might have A0, A1, A2, and A3. That's a 4 bits, right? Same is the case with B as an input. We'll be having it as B0, B1, B2, and B3, right? And then we are going to compare the two 4-bit. It is 4-bit, which we are going to call it as a then where we will find out which is equal or which is lesser or which is greater. Okay. So typically the IC that we will be having is something like this, the circuit diagram which is on the screen right now. Hope the screen is visible. Just drop a message in the chat box to let know, madam, that you are able to see the IC 7485. Are you able to see that?
Yes,
The
sir.
circuit diagram along with the is on the screen, right? Okay. So since it is 4-bit, we are going to use two IC 7485s in lab to connect them in series, and then we will be working on it. Okay. So that means each of my IC 7485 can use only two inputs of 2 bits each, right? Since I need a 4-bit 2 inputs, I'm relying upon two different two ICs, and I'm going to connect them in series, right? So when I connect one with the other, it is a series connection, and I'm getting an output which are only three in numbers. A is greater than B, or A is equal to B, or A is less than B. Okay. When you look at the truth table that is available below, you will be able to see that A is one input, B is another input. Each of the inputs are assigned with B0 to B3. It's connected as B4, but it should be only B3, and it is connected as A3. It should be only A3. Okay, since we are talking with respect to 4 bits only. So if both the inputs are equal, then in that case, when you look at your row number 3, look at the row number 3. Here you find 0, 110. The same is the case here, 0, 110. That means these two inputs are same. So that's why for an input output A is equal to B, I have a logic high as an output. Okay. Same is the case with the other one, which is lesser and which is greater. When I say here, right? So A value is 1,000, and the B value is all zeros. So that means A is greater than B. Okay, so A is greater than B is available. This is for A less than B, so the other one is available. So this is what is the case which we do it in our lab. But in this case of simulation part, we are going to use this logic uh, gates like AND gate, XOR gate, and OR gate, and we are going to compute this. Okay, so I have shared with you a link for the VLab on your chat box. When you can open to that, you will be able to find this as a page which is available to you, right? So this is here for a verification of a truth table of 1 bit and 2-bit comparator. We are talking about 4-bit, and right now here we have got in VLab as 1 bit and 2-bit only using logic gates, right? On the theory part, as I already said earlier, a magnitude comparator is a combinational circuit which is going to compare two digital or binary numbers in order to find out whether they are equal or less than or greater than the other numbers, right? So that's my objective. So functional block diagram is available here with two input A and B, and outputs are 3, less than, greater than, and equal, right? When I say it is 1 bit, then it is only A and B. Look at the first row, both the values are same. So you have your A equal to B as logic high. And same is the case when it is with the fourth row. A and B are same. So your A is equal to B is at logic high. When you come to the row number 2, 0 and 1, B is greater than A. Okay. So that's why this particular A is less than B is at its logic high. The same is the case with the other one, a third row, where A is greater than B. So this particular cell is now with the logic high. Okay. So when it is a 1-bit comparator, the circuit goes like this. Okay. And since we are talking with respect to a 2-bit magnitude comparator, in the Word file, what I have shared to you is a 2-bit magnitude comparator. Okay. So in a 2-bit magnitude comparator, this is how your output table is expected to be. By default, they have given us all the possible combinations are available. But in the lab component, I have given only 4 samples which you are supposed to find out. And mark its corresponding logic high or logic low. Okay. So this is what the truth table is, and this is the circuit diagram. Okay. The same is the logic diagram which we have given in the Word file also. Right. Getting into the simulation part of VLab, what you will be able to see is on simulation you have for both 1-bit as well as for the 2-bit. Okay, first let us go to 1-bit comparator. Under the 1-bit comparator, you have got two simulators, simulator 1 and simulator 2. Simulator 1, I'm going to use the ICs here, and in simulator 2, I'm going to work on with logic gates. Okay, so let's go with simulator 1 basically. First of all, first as always, switch on the power. Okay, then here what it means is now both the switch 1 and switch 2, namely your input X and Y, are at logic low, or both are at 0, 0. So that's why this LED, which is corresponding to an output of X is equal to Y, is glowing. Okay. So what I will first case, what I will do is I will immediately click on this add button and I'll make sure X is equal to 0, Y is equal to 0. So X is equal to Y is having an input 1 that corresponds to the glow of this LED 3. Right. Now let me make a transition of this switch 1 from low to high. What it means here is X is now 1, Y is equal to 0. That means X is greater than Y. So that's why you have your LED 1 is glowing. X is equal to 1, Y is equal to 0, X is greater than Y. So that is your logic high. Now let me go to the other transition. X is equal to 0, Y is equal to 1. X is equal to 0, Y is equal to 1, which means X is less than Y. Okay. And on the last case, when both are equal, 1 and 1. Okay. So this is the one table that you are supposed to find out. Okay. So this is with respect to one bit magnitude comparator. Okay. So same is the case coming here. You will have to put 0 and 0 here, and just do on your voice. A is equal to B now. So I'll put this as 0, this as 1, and this as 0. To check it, you will get a tables values available in the truth table with remarks, right? If in case this is with 0 and if I do it with this, and if I come to click it, check, yes, it's incorrect, right? So this is for an one bit comparator, right? So let us not focus on one bit first of let us focus on this only to get to know how this works, right? But our work is mainly on the 2-bit comparator, right? Click on the 2-bit comparator. Again, you will have your simulator 1 and simulator 2, right? On simulator 1, as always, supply. Okay. So here, this is X0 and X1 are 2-bit input X, Y0 and Y1 are the 2-bit input Y, right? So I have got X0 and X1, Y0 and Y1. Okay. And by default, all these are at logic low, right? That's the reason behind the LED corresponding to an output of X is equal to Y is at its glowing state. So click on add, you will find that thing to be available here. Okay. All that you are expected to do here is check on the word file. What is the input state that is available? All these 4 are 0, right? A0, A1, B0, and B1 are all zeros. So that is one state that you are supposed to identify in this case. So that is one case. Instead of A, here we have using X. Instead of B, here we are using Y, right? So this is the case what we just wanted to have. So X is equal to Y. So here you are expected to put 1 here and 0 on the other cases, right? So this is an expected answer in this box. Okay. And similarly, go ahead with the other cases of this values. Okay. I said A0 is equal to X0. So this is A0 is equal to X0. So that is at its 0 and this is at its 1. Okay. So in another case, B0 is equal to Y0. So B0 is equal to Y0. This is at its value. I'll click on that value, right? So here A is greater than B, right? So that I should put here. A is greater than B. 1, so 1, 0, 0, right? Similarly, complete the other 2 rows. And on the circuit bus, you are expected to string this file to the possible case. Only those 4 rows you can do. Okay, get those values. Okay, so this is with respect to the VLAB part. Okay, so this is with respect to the simulator. Here, click on this, you will get this logic diagram. This logic diagram is what you are supposed to practice in circuit bus and find its corresponding output value for the same. Right? So for simulator 1, take a screenshot, put it in a Word file. Simulator 2, take a screenshot, put it in the Word file. Right? And on the circuit bus, do this logic connections and give the input values as these values, these 4 values, okay, and find out the corresponding outputs on this pin, right? So on circuit bus, this is what is expected. So only this diagram, work it out on circuit bus, right? So as always, file has been shared with you, the manual part of your magnitude comparator. So you will have to write the inference result, all those things in the first file. Second one is your VLAB file, screenshot of your 2-bit magnitude comparator. Circuit OS file is a logic diagram with its corresponding output, right? So that you will have to do it and submit it with respect to the experiment number 5. Okay. Now let me know if you have in this particular experiment. Is there anything that you want me to uh, explain on this experiment? Experiment number 5. I'm looking at your chat box. Let me know if that experiment number 5 is clear. Hope the chat box is visible to you also. If you can drop an answer, you will find it easy.
Is it clear, guys?
Okay, Sedu. Yes, at least Sedu is there to rescue me. Yeah, thank you, Sedu. From the A section and B section, yeah. Satish Nagaraj, thank you. You are from B section, Sanmati from A section. Okay, fine. So that is with respect to the experiment number 5, right? Now let's move on to the experiment number 6. That is one of the simplest experiment that we are going to do, right? So earlier we have studied about the shift registers, right? So shift registers, we have got 4 types of shift registers: serial input, serial output, serial input, parallel output, parallel input, serial output, and parallel input, parallel output, right? So out of those 4 types, we are going to do focus only on one particular type, which is a serial input, parallel output shift register. Serial in, parallel out shift register, right? So that is our experiment number 6, design and implementation of a shift register. If in case we were in our lab, we might be doing all the 4 shift registers. But as of now, for the time constraint, we will focus on only one type of shift registers, which is SIPO, right? So for this, let me share you the VLab link. Okay. Okay. So on your chat box, you have both the a link for your next experiment, namely design register. Okay. So here, let's get into this part. Yeah. Okay. So here, as I said, we are going to design and verify a 4-bit serial in, parallel out shift register. Okay. By flip flop. A D flip flop is available with the IC number of IC7474. Okay. So to get to know about what is my SIPO on the theory part, I'll have a complete insight of what is available there. Okay. A D flip flop is there. I'm going to give an input, data input 1 to the flip flop 1. Data input is fed to my flip flop 1. And on the clock pulse, every time when I give a clock pulse, I will get my data transferred from this flip flop to the subsequent flip flop across each and every flip flop. Right? Do I make sense of what I'm saying? கண்டினியூஸா இருக்கக்கூடிய ஃபிளிப் ஃப்ளாப்ல ஃபர்ஸ்ட் ஃபிளிப் ஃப்ளாப்புக்கு நம்ம ஒரு டேட்டா இன்புட் கொடுக்க போறோம். ஓகே, ஒரு தடவையும் நான் கிளாக் பல்ஸ் கொடுக்கும் போது என்ன ஆகும் அப்படின்னா, அந்த அவுட்புட் வந்து வில் கெட் ஷிஃப்டட் டு த அடுத்தடுத்து இருக்கக்கூடிய அந்த ஃபிளிப் ஃப்ளாப்புக்கு அவுட்புட் வந்து ஷிஃப்ட் ஆகிக்கிட்டே போகும். ஓகே, இப்ப நம்ம கிட்ட இருக்கக்கூடிய ஷிஃப்ட் ரெஜிஸ்டர் வந்து சீரியல் இன் parallel அவுட் அப்படிங்கறனால ஒரு ஃபிளிப் ஃப்ளாப்போட அவுட்புட்ல இருந்து ஐ எம் கோயிங் டு டேப் அண்ட் சிக்னல் அந்த அவுட்புட்டை நான் டைரக்டா எடுக்க போறேன். ஸோ அது எப்படி அடுத்த ஃபிளிப் ஃப்ளாப்புக்கு டிரான்ஸ்ஃபர் ஆகுதோ அதே அவுட்புட் எனக்கு அந்த ஒரு பர்டிகுலர் பின் மூலமா எனக்கு கிடைச்சிட்டே இருக்கும். ஸோ தட் இஸ் மை parallel அவுட். If it is serial input and serial output, what it happens is it travels to here, then it travels to here, and finally clock pulse கொடுத்துக்கிட்டே இருப்பேன். கடைசியா எந்த ஃபிளிப் ஃப்ளாப் இருக்கோ அத்தனை clock pulse நான் கொடுக்கணும். அது அப்புறம் தான் எனக்கு இங்க நான் கொடுத்த இன்புட் வந்து அங்க எனக்கு அவுட்புட்ல வரும். சீரியல் இன் சீரியல் அவுட்ல. whereas in parallel அவுட் பொறுத்த வரைக்கும் ஒரு clock pulse கொடுக்கும்போது எனக்கு அந்த பிட்டோட அவுட் அந்த ஃபிளிப் ஃப்ளாப்போட அவுட் வந்து எனக்கு வந்துகிட்டே இருக்கும். Okay, so that is the crux or the theory part behind this serial in and parallel out. Okay, to get to understand that clearly, let us get into the simulation part. Where, okay, this is where you have your okay. Hope it is visible completely. Yeah. As always, let me click on the battery to make it connected. Yeah, now the battery is connected. So what I'm going to have is now the input is not given. Okay, so default it is at no output is available. Let me
Sir, no audio, sir. Shiva, sir, no audio.
Somebody let me know at which point I got disconnected.
Sir, it's
Guys?
not shared in C section.
Yeah, it is shared, I suppose. No,
Are you
it's
able
getting
to
shared, I
see,
suppose. Just a
guys?
minute, madam. 1 minute.
Now it's coming, sir. You were explaining about the shift registers, why we are going for serial in parallel out, how we are getting output in that. Theory portion.
Simulator இந்த பக்கமே வரல இது வரைக்கும்.
Just
Did I
it
explain
just
this?
came to here, but immediately it is. Uh, no, I think you have to from start. You have to do.
Okay, I'll start from here. Okay. Sorry. That's a nice situation, like speaking to no one,
Theory part is over, sir.
thinking of speaking. Okay. Yeah. Now coming back to this one. Okay. So, okay.
Simulator.
Now, hope the screen is visible. Yeah, okay.
Yes, sir.
First step is connect your battery. Okay. Then, initially, this is a point where I'll have to click on my data input, right? And this is a point to initiate my clock sequence. Right now, I have not touched both these points, right? And what the ICs that I was speaking about is for IC 7474, and each of these ICs are accumulating two D flip flops. Okay, so internally you will be able to find. Okay, here you will be able to find IC 7474 is having two D flip flops. Okay, so the input to the first flip flop is coming from the pin number 2, which is coming from the data input. Okay, and the output of this flip flop Q is coming out to pin number 5. Okay, and the same pin number output 5 is tapped here, and it is connected through pin number 12 to the input of the next flip flop. Hope you are able to travel with me. From pin number 5, I'm just tapping on this line of contact, hitting at pin number 12, getting back to my second flip flop input. Am I there?
Sir, the circuit
Okay.
is not visible, sir.
Circuit is not visible.
Only the lower part is unable to see.
Only
Lower part is unable to see.
now.
That part.
Now,
Now the upper part. Okay, little bit more slowly, sir. Down.
okay. Is it okay now?
Is it okay now?
Okay. No, we will just tell them what to do, and once when they are clicking on the link, they will be able to.
Okay, fine. Okay, fine, sir. Okay.
Okay. So, initially, I have not disturbed my input, so it is at 0, and I have not disturbed my clock pulse. Again, that is at 0. So I'll just add this value. So that is my first serial number. With clock is 0, input data is 0, and I'll be able to find. Since I said it is a 4-bit shift register, I need to have 4 D flip flops. So as I said, IC 7474 can hold only 2 D flip flop. I'm going to use 2 IC 7474 in series connection. Okay. So each of the output which I'm going to get it from pin number 5 is one output of my first flip flop, and the output of second flip flop is always coming from pin number 9. Same is the case with here. Pin number 5 output, pin number 9 is again another output. Right? Those outputs are here connected to the LEDs for work. So next serial number, what I'm going to do is I'm going to now switch on my data input. Okay. but I have not touched my clock pulse. If I add this value, you will be able to find, even though I have given my data input here, when there is no clock pulse given to the ICs or to the flip-flops, you will not be able to find an output transition happening, right? So what it means is, even though there is a data input available there, unless otherwise you give a clock signal, you cannot get an output. Now you will be able to look at, I'm just going to give a clock pulse here, okay? Immediately you find a LED glowing. That means the clock pulse has gone to all the 4 flip-flops, but the data input is available to the first flip-flop. So that first flip-flop is giving an output, right? So that I'm adding here. The input data is now available. The first clock pulse is also available, which is giving an logic high state indication to my Q3. Okay. Now I'll give my second clock pulse. You see, Q2 is glowing. That means the output of this has now traveled to the second flip-flop as input. And since the second clock pulse was given, this D flip-flop is giving to an output from pin number 9. That is also I am adding. This is my second clock pulse. Same input data is available there. This is my third clock pulse. I'm adding. Fourth clock pulse. I'll add it. Right? Now is that since it is 4 bit, now I have given 4 clock pulses. So after this, what I'm going to do is, now I'll change the serial input to 0 now. Okay. Then I'm going to give a clock pulse now. So this is my 5th clock pulse. Okay. As I'm giving my 5th clock pulse, you will be able to find 5th clock pulse. Input I have changed from 1 to 0. So the first flip-flop output is now getting to be 0. Now, 6th clock pulse. Add. Input is 0. Q2 is now 0. 7th clock pulse. 0. And the last, 8th clock pulse. Completely 0. Right? So this is the case which you need to understand. Likewise is the one in which we can do for all the 4 flip-flops. In lab, when you are able to do the shift registers, you will really enjoy doing it, right? So every time when you give a clock pulse and you change your input data, you will be able to find. But the only problem lies in the identification of the pin number and its corresponding connectivity to your common ground and supply, and tapping the output from the corresponding pin. Once when you forget the pin number, of course, any procedure that you follow, you will end up with a different answers only, right? So for this experiment number 6, that is all with experiment number 6, right? So all that you will be doing in experiment number 6 is, yeah, here. So this is the diagram for it, right? So since we said it is parallel out, A, QB, QC, and QD. So for the first 4 clock pulses, for this particular data input, you are expected to fill this table, right? Fill it. There are few prerequisite question, answer it, write the inference and result. Again, we remind you, for all the experiments that you do, just click on this area and don't forget to mark the date on which you are doing it, right? This, even after repeatedly telling, we are unable to find the date which is mentioned on your submission copies, right? So on the submission for experiment number 6, one second. Yeah, number 6. There are only 2 requirements. There is no circuit file. Okay, so just submit the Word file that is available to us in this lab experiment 6 roll number .docket, and this VLAB file, which I mean is this one. Okay, so once when you are completely picking up these 4 states is quite sufficient. What I have mentioned here, right? For these 4 states, 5 states, right? 0 clock pulse, 1, 2, 3, 4 clock pulse for the first 4 in data input at logic 1, and for the 5th clock pulse, it is at logic 0, right? Get the corresponding output, fill it. Okay, so for that, you can just take a screenshot of that. Okay. For that alone, minimize it, right? Take a screenshot, save it as an image file, and submit it. Only 2 files are need to be submitted for experiment number 6. Whereas for experiment number 1 to 5, you have submitted um, 3 files. Okay. So on click, you will find the due date of today. We have a quiz, and for due date of Sunday, we have experiment number 5 and 6. As of now, for quiz section C, 20 students have turned in, 25 are still pending, and as far as section A and B put together, you have 41 turned in and 44 are still to submit it. Right? Submit it at the earliest and complete your task. Okay. So I suppose with this, it's 3:22. If there is anything that you want to have as a clarification for this lab components, now is the time for you. We want to attach simulation. Just a minute. Yeah, we want to attach simulator 2 also. Sir. No need of simulator 2, do only for simulation 1. Simulator 1 is sufficient. Okay. But work out on simulator 2 also and understand how the process is happening. Okay. Any other doubts, clarifications? Was that clear first of all of what I was explaining for experiment number 5 and 6? Makkale? Can you speak out something? Yes. There are only few people who are just speaking out at all times. Is that clear?
Is that clear, guys? Yes,
Malavika,
yes, yes.
Saranya.
So many yeses coming.
Okay, fine. So that is all from us from right now for today. Morning, madam was taking on conversion of flip-flop from one to other. And right now she has taken 2 problems on counters. Am I right, madam?
Yes, sir.
2
Yes, sir.
problems. And Saturday class we might be doing on design and analysis part of it. Okay.
Synchronous and
So,
asynchronous.
yes, it's an asynchronous circuit. That is all from all of us right now. So today, start the recording right now. Okay, fine. Sedu?